Hello and welcome to 29th lecture of the course on corrosion, environmental degradation and surface engineering. So, finally, we are in last phase of this course and the topic of this lecture is a surface engineering. It is an interesting title, the reason being we have been discussing that most of the failures will be happening on the surface. Even the material which is going to get damaged, 70 to 80% damage happen to the surface or maybe initiation happens at the surface. The question comes, can we really engineer the surface? Because surface engineering means that we need to engineer the surface so the surface degradation can be reduced to minimize to the almost negligible level. Then question comes, what is the meaning of the surface? And different literature give different definition to the surface itself. One literature indicates that the top 2 to 10 atomic layers or molecular layers will be treated as a surface. That means the top 0.5 nanometer to 3 nanometer layer will be only treated as a surface, otherwise it is not surface. Second literature says anything which is having a layer thickness lesser than 100 nanometer should be treated as a surface, otherwise it is a bulk solid state properties. Anything exceeding 100 nanometer is not a part of the surface. We will be thinking slightly different manner, but before that we want to really know how do we engineer the surface. So, for that we say that we need to improve surface qualities. Now, in surface quality again we have a sub classification. What will be the chemical composition of the top surface? What will be the morphology of the surface? And what will be the structure? Is it sp2 structure, sp3 structure, what kind of a structure we want to award or we want to give to the surface. So, this is completely novelty of this course, that we need to think about engineering the surface, making the surface a kind of interface between environment and the functionality, and then separate these two so that degradation comes to almost negligible, and that is why this lecture is important, and next 3 lectures also will be in the same tone. Now, what we want to do here, improving the surface quality to achieve desirable functional qualities. What are the desirable functional qualities? Minimize the friction, minimize the wear, minimize the corrosion, minimize the erosion. There should not be any damage of the surface. So, these can be a functionalities also, and whatever the performance enhancement, whatever we are doing can we really enhance. So, we need to have a lot of literature review, study, and then think over how do we continuously improve the performance. Maybe we are already using some surfaces, but how do we improve that performance, that there should be some sort of the quantification, measurement, and then we can think about enhancement. So, in short I can say the surface engineering basically is a fabrication of surfaces which can really provide a higher durability, higher wear resistance, higher corrosion protection, better tribological characteristics. And how do we do that? By modifying surface at the atomic level, molecular level or microstructural level. So, if I am thinking about surface layer as a 0.5 to 3 nanometer, naturally I had to think about atomic layer or maybe to at most to molecular layer. However, when we think about 100 nanometer, 0.1 micron, we can think about a microstructural level. So, this depends on the word whether we are thinking about the microtribology, nanotechnology or microtechnology kind of activities. So, what are the different approaches of the surface engineering? We say there are 3 main approaches. Can we go ahead with the coating? A kind of other surface, we coat on the surface or maybe the subsurface which we really require, and the coating can be like 100 nanometer or maybe even a few microns. Or can we think about the surface patterning? Can we really make it? Or can we really do a surface treatment? However, surface treatment is one of the common in mechanical engineering. We try to treat the surface so the desirable properties can be awarded to the surface itself. Now, before starting this whole topic, first, which is a key aspect of the surface, is a surface roughness. And we know there is established standard for that, that is the ISO 4287. That standard define all the parameters related to the surface roughness, and then we will try to connect this with a surface engineering in the present lecture. So, what is the surface roughness? You see, basically surface roughness is related to irregularities on the surface, and we know most of the damage on the surface happens because of the irregularities, and irregularities really look very awkward at the micron and nano level. You are able to see this complete surface, and there is a red color line as a mean line in that. So, this is a typical surface profile or roughness profile. So, what we do in this case, we say surface roughness is refers to how far surface deviate from a perfection. So, if I am assuming the red color is a perfect line, this is the surface line, how much deviation is happening from this surface, that is the peak side and valley side also. So, negative and positive both, right. So, we say term surface roughness refers to how far the surface deviate from a perfection. Surface roughness naturally will comprise some sort of scratches. So, this roughness can come because of the scratches, because of the tool wear, maybe because of the tool is not very sharp, it is a blunt, right. So, those kind of things, or maybe possibility of the pit formation at the nano level or micron level, possibilities of the grooves or so on. So, there may be a number of faults, number of defects, and we know very well that any defect on surface will create some sort of initiation of the crack or maybe stress concentration, and that stress concentration will lead to the corrosion or will enhance the corrosion rate, and that is not really acceptable from a sustainability point of view. Now, we can say the surface roughness can be quantified, can be measured using some sort of profilometer. Profilometer can be a contact type, can be non-contact type also. So, what we do in this case, we try to figure out what is the vertical displacement. So, if I am taking this as a red color line as a mean line, so what is the vertical displacement in a negative side and positive side both, right. And then if we are thinking about a stylus, which is a kind of a contact device, or maybe some sort of a diamond tip prop across the surface, how do we really move in a one direction and then keep measuring the vertical distance? Now, it can be 2D, it can be 3D. We generally prefer in this the 3D profile, because we know that context needs to be made at the 3D surfaces. It cannot be on a 2D surfaces, and 2D surface will not be able to really give clear cut idea, particularly when we are thinking about the digitization, when we are thinking about the data driven approach. 2D will not be really able to help us much, but from understanding point of view, from concept point of view, we may require a 2D also. And what we say, a rougher surface will have a larger deviation. So, larger deviation means rougher the surface, right. So, these are the some sort of a thing which already you may be knowing, and then because of surface roughness, in our first lecture itself I say that many times the nominal contact area reduced to the 1% of the area only. We do not really get a complete area, and that is why the almost every asperities goes through the plastic deformation. Even though in mechanical engineering we assume load is too low, and then it will be subjected to only elastic deformation. In reality, every asperities goes to the plastic deformation and causes some sort of the modification in roughness value. So, this is one of the example has been given where there is we have shown a stylus, and a stylus can travel, and maybe stylus has started from this position, this line is starting position, and then it is ending at the finishing position over here. So, this is the initiation and the finishing position, and we are able to see that stylus position. Now, depends on the radius of the stylus itself, we will decide what kind of surface roughness will come. If it is a pinpoint, it is very sharp, then we will find out the true surface roughness. If it is not so, then quite possible it will have, this stylus will have some sort of radius, and then that will affect the accuracy. So, depends what we are really using, which kind of a stylus we are using. That is why this profilometer can be very low cost, is something like a 2 lakh rupees, or it can be very costly, maybe like a 2 crore rupees also. So, there is a variation and then kind of accuracy and the 2D or maybe 3D and what kind of parameters we require when we want to really compare, we want to really design something, can it really give interactive surfaces also. So, in this case what are the different things which we are able to see one name here, something is called evaluation length. So, what is evaluation length we will be considering in this lecture. So, when we think about the quantification of surface roughness, we have a number of methods, but we prefer to go ahead with the digitization, because in these days what we do, we pick up the points on line and then try to calculate the values. So, this is the digitization method and this is what we say average surface roughness. What we are using, we are taking absolute value of every z point or every height, whether there is a negative side or positive side with respect to surface, but we are taking absolute value. So, we do not get a negative value in this case, and then whatever the mean value comes out of this. However, one point interesting point is that surfaces may have two kind of things. One is what we are considering the roughness, another one may be the waviness also. However, we know that when we think about the microtechnology or nanotechnology, mostly waviness is rejected, because that is on a higher amplitude side. We concentrate only on surface roughness. Here we have also showed analog approach, maybe the continuous approach. We are integrating z and then z square x as a function of the x, or the 0 to 1, that is the evaluation length or sampling length. Here we will be using the word sampling length, and then what is the difference between sampling length and evaluation length, we will be discussing those things also. However, if we have zx as a function of x, then going ahead with this kind of integration makes sense. Otherwise, we will again go with the digitization, we will go ahead with the summation and then divide by the number of points which we are accounting in this case. However, there are two values, we say RQ value, that is a root mean square value, and there is another one RA value or RA surface, RA roughness, that is the average surface roughness. So, they are, we are talking about the two, one is RQ, other one is RA. In manufacturing, we prefer to use RA value, almost all the manufacturing processes they define RA value. However, from a surface engineering point of view, we prefer to use RQ value. What is the reason as such? Because when we are thinking about designing the surface, we really require some sort of characteristics of the surface, and that will be more signified with RQ value compared to RA value. That is why we prefer to use RQ value compared to RA value. Just to differentiate these two, or maybe just to elaborate on what I said, I am showing two figures. This is a figure 1 and this is a figure 2. You can see here in the figure 1, we are showing the bad bearing, good bearing. In both the values, in both the case, value RA value is 0.25. It can be angstrom, it can be the micron, it can be nanometer, but RA value is the same. Question comes, what is the RQ value? In this case, RQ value is a 0.58. It can be angstrom, nanometer or micron, and in other case is a 0.37. And we know very well roughness should be as low as possible, should be minimum. So, that way this value is a good value, is a preferred value. Even though RA value is same, I will choose this surface, and this surface has been designated as a good bearing surface. Reason being, it does not have a sharp peaks, it has a values, and these values can act as a dust pit. So, they collect the debris there, and then they keep ultra mild wear, ultra mild wear itself. Even the corrosive product which are coming out, maybe they get delaminated easily because of the brittleness, those particles also can come and reside in this kind of valleys. So, it will not interfere in a work, and that is what we want. That is why this is this surface is a more important, preferable compared to this surface. Same thing has been shown in this figure 2 also. You can see here there is a very high peaks. which have a very high stress concentration also, effective area of contact will be low and the stress will be very high. While in this case area of contact will be less on the more and then the stress level will be lesser, and then again as I mentioned in a previous figure that this act as a valleys and then that will be useful. Even in both the cases the surface roughness is almost same. In this case is of 2.4 first case and the second case is 2.5 micron. But here we are talking about angstrom level and here we are talking about the micron level. So, it can vary from angstrom nanometer to the micron side. Now, we also had the first slide we mentioned something like a ISO standard, that is a 4287 and that gives the surface roughness parameters. And what are those surface roughness parameters? There is a long list, but we will just focus only on the 5 parameters, that is the RA value, RZ value, RQ value, RT value and RP value. RA value and RQ value was demonstrated or maybe the shown in a figurative manner in the previous slide. However, we are trying to repeat over here. We say it is a arithmetic mean roughness and average deviation of the surface roughness profile from a mean line. RA is calculated as a arithmetic average of absolute value, that is what we showed in a Z value, that absolute sign, that absolute value of all the measured profile heights. Now, interesting point, this is done on the sampling length. Coming to the next one, we say RZ, we take a 10 points and then 10 point roughness, and then this in this case also we take absolute value of the peak to valley. Now, here the 5 we take a highest peaks and 5 we take a lowest valleys, and here we count something like a evaluation length, which is different than the sampling length. So, RZ is done mostly on a bigger scale compared to the RA value. So, there is a basic difference, and RZ provides an indication of the height difference between the highest peak and lowest valley from the evaluated or within the evaluated section. So, if somebody asks what will be the surface in the layer or maybe top layer, I will say better you go ahead with the RZ value. Now, if RZ value is 20 micron, you treat this surface as a 20 micron, and in fact, it can be more also if the RT is on higher side, right. So, those things are also possible. However, I prefer to go ahead with the RZ if the surface roughness or the surface to be defined in a dimension. Now, coming to the RQ value, in this case it is as I mentioned earlier, it is a root mean square roughness, and it is a basically profile height deviation from mean line, and again it is measured over the sampling length. It gives a overall variation in the surface roughness, and always it will be always RQ value will be higher than RA value. Now, coming to the RT, we say the total surface the total height roughness, this is the vertical distance between the highest peak to the lowest peak, but within evaluation line. So, in RZ value we were choosing 5 highest peaks and 5 lowest valleys, while in RZ we say no, highest peak and then maybe say deepest or maybe the lowest valley. That is what we want to go ahead, and again we are measuring over here on evaluation line. So, 2 length we will say sampling length, we use RA value and RQ value. Coming to the evaluation length, we measure the RZ and RT value. Another last one parameters in this case is the RP, which is the maximum peak height, highest peak within evaluation length. So, is another one we try to go ahead with the evaluation length, and RP indicates maximum peak height on the surface. More or less what we say, the RZ or RT are important from defining the surface roughness, from defining the surface point of view. RA and RQ value are defined are important from the roughness point of view, or maybe to compare two surfaces. However, if the two values almost same, then we may require other surface roughness parameters also. Here we are not defining kurtosis value, we are not defining skewness values, which we have defined in our earlier lecture, and then those values are important to dig out what are the defects also. So, for the good surface, we do not worry about skewness, we do not worry about the kurtosis. But for the bad surface, for damaged surface, for degradation surface, we really worry about those. We need to figure out those values also. And as in this case particularly, all the parameters are generally defined in the micrometer range or nanometer range, and then this is a basically quantitative measurement of roughness. So, it is very important to understand these values. Now, let us see what are the evaluation length, what is the sampling length. We take first the traversing length, then comes the evaluation length, then comes the sampling length, right. You are able to see here the sampling length is the smallest one, evaluation length comes somewhere in between, and transversing length is a large one, big one, right. And then by and large we require 5 samples to figure out what will be RA value and RQ value. So, that is why the evaluation length, that is L, is equal to 5 into small length, that is a sampling length. So, sampling length is the smallest one, evaluation length is the 5 times of the smallest length, and traversing length is the 7 times, that the traversing length, if I say TL, is the 7 times of the sampling length. Why do we really take a 2 extra length in this case? Because here when Stelis mounts on the surface, there will be some sort of deviation because of the edge load, and similarly when it comes out, again there is a possibility of the deviation. So, this first value and the last value should not be counted, because that is going to really affect the results. That is why our algorithm, whatever the profilometer we use, those profilometer, they will have inbuilt algorithms in that, and that is really accounted. Now, this is one of the surface roughness profile has been shown to you, and if you look at the profilometer reading, there is a LC, that is a sampling length, there is a LT, that is a transverse length, that is what I have shown over here, and there is a LM, that is a measuring length, that is a evaluation length, right. You can see here this LC is a 2.5, LT has to be a 7 times of that, that is what comes out to be 17.5, and LM is a 5 times of that comes out to be 12.5. Here the roughness RA is something like a 0.1 micron. As I mentioned, that RQ will be always larger and be a higher side compared to the RA value, that is why here it is coming around 50% more, is a 0.15. RZ is somewhat coming out to be the 1.1, and the highest peak value is somewhere 0.4 micron, right. So, this is a RZ itself varies from almost 1.1 micron. Naturally, we cannot say the surface is existing only on the top 3 nanometer, there is a big deviation, there is a valley also which is a part of the surface itself. So, we cannot neglect that, and that is what we need to really think about this. Now, as per this, according to the standard ISO 4287, sampling length should be specified along with average roughness. This is another important thing. If you change the sampling length, there is a possibility surface roughness value will change. So, there is a standard ISO standard which defines, okay, for this roughness, this may be the sampling length. If the roughness goes on higher side, we will change the sampling length. If roughness goes on smaller size or lesser size, again we will change the sampling length. So, it is basically iterative procedure. It is not a one go, you just mount a profilometer and get a value and be happy. Not like that, we need to really look at the standards, so that there is some kind of we say that across the world people are using the similar kind of the measurements. It is not somebody says my roughness value is 0.1 micron, and another lab say, oh, that instead of 0.1 micron it is a 0.2 micron or 0.05 micron. So, we want a standardization, and that is why we follow ISO standards. Now, I am just trying to show something on this. Here we picked up the one a metal surface. You can see on this side, this is the metal surface, this is the metal surface, and we mounted a profilometer on this. This is the profilometer with which we are able to show in this view, and this is a surface roughness profile. Can see means looks like a kind of a lot of noise on the surface, and in true sense every surface is this kind of characteristics. On top of that, we are saying we want to design the surface. That means we want to play with this kind of noise and make this noise more useful, more fruitful, more beneficial for the to avoid the surface degradation. If you look at this case also, the RA value is something like a 0.6 and RQ value is a 0.76. Again RQ is greater than RA value, and then here RP is something like a 1.85, RZ is 3.63 micron, huge difference, right. So, these are the values, and then depends on the which kind of profilometer we are using. This table may vary little bit to this side or that side. I have a small thing to show. There is a one video I am trying to show. So, this is what Pestrolus is moving on the surface, and we say it is and then the loading and unloading times we need to really look at those. Now, let us start this topic. We say the surface engineering to modify surface roughness, to improve the surface roughness, to really play so that we get a better surface or better feature. That is why we say the functional features including wetting behavior, where the surface will get wet easily, will absorb the moisture, or maybe they can keep the moisture for a longer time, or improve the topological surfaces like a friction and wear surface or optical characteristics. All these are possible using the surface modification or surface design, and sometimes we call it surface texturing. We texture the surface, and fortunately this slide also shows some sort of texturing on the surface. We are able to see some sort of projection on the surface itself. And then this slide also was shown in earlier lecture. We say depends on the tool movement, we may get a surface texture in the horizontal direction, surface texture in the vertical direction, in the crossed one, or maybe the diamond shape in the multi direction also. And everywhere the friction will change, everywhere the wear characteristic will change, even the corrosion behavior will change. So, just by moving tool in different manner, different orientation, we can really get some surface which may be harmful or which will be maybe beneficial. So, why not study in a manner we get only benefits, not harm. That is why this topic is important. Now, this surface is also shown earlier. You can see here the multi dimples in the surface, and we know the dimple has a kind of a curvature on surface, so stress concentration will not be significant here. In addition, they may have a number of dust bin or maybe some sort of pockets to keep a reservoir of the oils also. So, this kind of surfaces are really playing important role in a number of the products. So, we can say the surface design is a process of manipulating surface structure to generate a desirable surface parameters in order to reduce the surface failure due to wear, due to erosion and due to corrosion. If you are able to play with this, if you are able to do really like this, naturally we will get a desirable results. Now, how do we do that? What we are talking about the manufacturing, now we are talking something like a micro manufacturing. Can we go on a micro manufacturing? And the laser texturing is one of the micro manufacturing process. Microelectric discharge machining is a micro manufacturing process. CNC ultrasonic machining is a micro manufacturing process. Chemical etching, electrochemical etching, or maybe a number of other processes also are there. We are not going to describe all, but we will be highlighting few processes so that we get understanding how and then the surfaces are really getting changed to the desirable side, so that we get a more and better feature. So, why texturing? I believe that we do not really require now to discuss about that. You may be already very familiar with texturing is essential, texturing is very important. However, in the tribology we have several examples. Examples can be from different streams. In this case, we have given example of the piston ring, thrust bearings, and there are many examples, and in this case basically the micro dimples which we showed in the previous slide also, and organized in some sort of structured manner and matrix manner or arrays manner, they really reduce the friction, they reduce the wear and increase the surface life. So, sometime we were talking initially only 5000 hours cycle life, now we talk about the 50,000 or 15,000 life cycle also, just by tuning the surface, and that is the beauty of the surface engineering. We say surface this textures serves the three key roles, particularly in the tribology and in domain of the lubrication. It traps the debris, so keep ultra mild wear in ultra mild wear. It does not cause to increase the wear rate because of the trapping of those particles between the interface or maybe at the interface between the surfaces. So, this acts like a pocket, and whatever the debris it get dumped there, and I use a word, it can act as a dustbin. And then this can act as also surface to keep a reserve of the lubricant, even in between some pump fail, at least we know the lubricant is there. So, the product will survive for some more time. And then it sometime, because of there are pockets and then there is a pressure generation, these pockets also work as a micro bearings. So, three main characteristics of this texture surface, we say they act as to capture or to trap the debris, to keep a lubricant reservoir, or act as a lubricant reservoir, or maybe acting as a micro bearing also in the surface. Now, what is the difference? As I mentioned, the mechanical machineries or maybe the mechanical machining techniques, something like a milling, turning, grinding, which we have been using, sandblasting, even also used for the surface finish operation, can produce various patterns, no doubt. This mechanical machining process can develop the patterns, but on the larger scale, if we require a nano scale, a micro scale, I will prefer not to go with this kind of mechanical machines. We really require a micro machines, we do not go with the mechanical machines. Now, there is a one process, in this case chemical etching, which that is why we do not go out of the mechanical micro machine, but chemical etching. Here what we do, in this case we selectively remove the material by putting some sort of mask and then treating the surface. So, in this process of the selectively removing the material from a surface using the chemical agent, remove chemically surface from selected portions. So, this specific pattern and the texture can be generated, they can even change the chemical composition of the surface, and then even different can be, then the surfaces can be generated by if we changing the etchant concentration or maybe even chemical composition of the surface or the etchant. So, what we are using etching agent, if we are using that, and then chemical composition and concentration can be changed, and then this also in process change the chemical composition of surface also. So, this approach is ideal for producing the micro nano scale texture, and then it can really maintain high precision, repeatability. However, whenever we do a masking, whenever we do some sort of selective remove of the material, there will be some deviation at the surfaces. So, if somebody says it is a very good surface, I will not be count with that. We may require post processing after that also. So, chemical etching may give very good surface precision, but we want better, then we need to really do post processing also on that. Now, there is a another thing which we also use, we say we first putting the layer and then we are chemically selecting it and we are removing the some portion of the layer. It can be 25% removal portion, it can be 30%, it can be 50% also. So, why do we really do that? Why not we go ahead with additive manufacturing itself? Wherever we require to deposit material, you deposit. Why you want to remove the surface? Why you want to go with a more and more wastage of materials? So, when we think on when we have considered like a life cycle assessment, we know what is really the trash which is coming out of the surface. right. From that point of view, I believe that additive manufacturing will be a better option, but question comes, will that be acting accurately, precisely? That is where we require more and more development, more and more innovation. So, this is the future, a kind of like a 3D printing make in a manner, so that surfaces really get a very good, the surface gets a top good layer within the nanometer or the few micron level, and that 3D printing can do faster. Reason being, when you print something like a 5 mm, compared to that, if you want to really print only 5 micron, actually additive manufacturing will be able to give better results, provided we have a good CNC machines, or maybe say that we have a strong maybe say very high stiffness of the system itself, and then it is also that whatever we are depositing, it is not really getting delaminated. So, addition is very strong there also. So, once we really remove hurdles or drawbacks of the existing additive manufacturing processes, I am sure this is the future. It will be really very useful in the future for to replace maybe to play major role in a surface engineering. So, in this case, we can really think about a specific patterns on the texture and then the printing form. Additive manufacturing allows for the design flexibility. We say that it can really go ahead provide a more and more design flexibility. Materials can be changed, chemical composition can be changed, temperature can be changed. Those things are possible, and it can be really providing some sort of customized texture even on the complex surfaces. So, these are the very high advantages, but we are waiting for the very good foolproof additive manufacturing technology, which may be happening in the future. Now, let us talk about something which is the two well known manufacturing processes, particularly for complicated texture patterns. One is called a laser based technique, other one is electrochemical. What I previous slide we mentioned about chemical etching, here we are talking about electrochemical etching. While in the laser ablation is basically removing the material, again it will have two divisions. So, what are those things? So, we say laser ablation removes a material from a surface by using concentrated laser beam. We know very well the laser beam is very concentrated, and then from wherever the material removal is required, removes the material from there, and it really produces the good texture. And we really carefully adjusting laser intensity, we can think about a variety of patterns, variety of the shape, variety of the depth possible, and making a very appropriate for the nanoscale texture or micro scale texture also, right. And then this can be utilized, laser ablation process can be utilized for even for metal, for ceramic and plastic also. So, it is a versatile, same setup can be used for the many materials. On top of that, it really provides a very high accuracy. Of course, cost is on the higher side, laser ablation cost will be on the higher side, but then the overall if we are really utilizing this machine for the several hours per day, this cost may be we can get back in a few years time. So, there are two surfaces, very complex surfaces has been shown you, that you can see here this is the texture surface. In this case we have made a number of pockets here, we are trying to show some sort of a very regular pattern, but many like that, there is a good number of arrays on this. So, this has been shown as one of the texture surface. Now, what are the different kind of the textures? There is a lot of literature available on that, and people have done, and unfortunately same texture, one author will say it is good, other author will say it is bad. What is the difference? Good in some circumstances, bad in some other circumstances. So, we do not have a generalized pattern or generalized texture which is the best for all the situation. They have a good situation, and then the pattern is good for some situation, but it may be bad for some other situation, and that is why we really require a thorough literature review to understand all those things. So, if we have picked up this figures, maybe next 2-3 slides also from this 2016 publication, and the name is the surface texture manufacturing techniques and tribological effects of the surface texturing on cutting tool performance. Here we are talking about the cutting tool performance only, not for the workpiece. It is a basically cutting tool. And then here the in first case they have shown a segment, each segment is around 150 by 150, right. So, this texture surface we say is not able to reduce adhesion, and particularly for the aluminum cutting, reason being the whatever the aluminum chip, they clog this kind of texture itself. So, there is no room as such available, and then this texture gets spoiled very fast, and it also increases because of the clogging of this texture. Because of the clogging of the texture, particularly with the chip, the friction coefficient increases significantly. So, in this situation we say 150 by 150 micron texture is not recommended. That is why we say here. So, reducing the dimension may solve the problem. That is what the literature indicates. So, another one now coming to the depth, 100 to 150 nanometer, spacing 700 nanometer. In this case again we are saying that the anti-adhesion property of this sine wave shape, this has been shown a sine wave in the something like this. Sine wave texture is in the found to be, in this case particularly anti-adhesion property is found to be less compared to the linear banded groove, and this indicates that cutting fluid which is required for the reducing adhesion which is required in this case is a increase, and then oil retaining capability is increasing to some extent in this case. If we are able to reduce the dimension, oil retaining capabilities can be increased. However, it can be subjective also, because we know oil will vary. Now, the cutting fluid, what kind of cutting fluid has been used? What is the really properties, what are the properties of the cutting fluid? It may again work for the some cases, it may not work for the other cases. Now, similar depth, similar spacing, there is a other one. Say instead of here we are talking about aluminum cutting, we come to the steel cutting. We say because of the high contact forces, these texture with the dimension were found to be useless. So, for aluminum it works well, for steel it may not work well, right. So, that is why we really require more literature or literature study or thorough understanding. The same piece may work for one situation, may not work for other situation, right. So, but however, we required some patterns, we know that what are the different kind of the texture patterns, and then what will be the behavior, and then if we do not have a knowledge, then we need to really conduct initially pilot study to come to understand and then come up with a judgment which pattern will be a better solution. Now, in this case what we say, the surface texture can be classified either under grooves or intermediate pits and dots. So, these are the intermediate one and these are the grooves. We can divide disconnected dimples, and that the way maybe we will show in the next slide. Disconnected dimple texture reduces the wear more efficiently than linear connected grooves. So, this groove will have a slightly higher wear rate compared to the disconnected texture, and then sometime because we are able to see this texture. Now, if I embed solid lubricant in that, it will act very nicely. So, friction, the coefficient of friction will come down significantly, even the wear rate will be significantly down, because solid lubricant will be sticking to the opposite surface, and the wear rate will come drastically down. So, that is why we say the solid lubricant present in texture reduces the friction and adhesion by forming a dynamic film on the contact surface. So, we do a texturing and embed some sort of solid lubricant. The retainability of the solid lubricant in those grooves or not in the grooves, and then the texture will be better compared to the other surfaces, or maybe otherwise utilizing the solid lubricant as it is. So, for filling the channels with MOS2 solid lubricant improve the wear resistance, it can be achieved. We say the connected texture like a grooves such as groove allow lubricant to flee, because this you can see here, if the lubricant is here it will pass easily. So, it will get drained. If I have just perpendicular to that, maybe there is another layer also on the surface, naturally lubricant will get trapped, it will not be skipping. So, that is why we say connected texture such as the grooves allow lubricant to flee, tribological contact and decrease kind of lubrication or hydrodynamic pressure generation will be less and worse from lubrication point of view and wear point of view, right. So, this kind of the long grooves may not be good. If you go with the perpendicular grooves also, or maybe say the texture in a manner, so that we get this kind of cross pattern, that it will really reduce the coefficient of friction in this manner. Now, as I mentioned that different kind of textures are there, is a pit shape, dot shape, banded grooves, but grooves we have already explained. Now, here the different references also have given that their width and the depth dimensions are different, then again the behavior will change, behavior will not be same. So, that is why we say this really required a good knowledge of different kind of textures, so that we get a better and better results. Now, let us take a dot type here. Dot type cannot really dot type reduces the friction and normal force compared to untextured tool. We are comparing with untextured, it is good, but it will be less effective than the pit type of texture. Now, if this is a pit type, it is here we are able to trap the lubricant, while in this case spacing is more, that we are not able to trap the lubricant. So, naturally dot shape for the lubrication purpose will not be as good as a pit shape. However, compared to the smooth surface, compared to the vertical grooves, naturally dot shape is very good. So, from that point I will say, if I put a vertical arrow, performance will improve significantly. Of course, the cost also will increase in this manner only. Now, let us take a couple of manufacturing processes. This is about the texturing process. First texturing process has been shown, a femtosecond laser micro machining process. In this situation, what we are really developing is some sort of a laser beam focused on a surface, and then it can be masked, it can be without mask also, and depends on what kind of surface we are developing and what kind of energy we are trying to give. So, there are two processes. In this case, we are saying that is basically laser beam fabrication. Sometimes we use a word laser texturing or laser surface texturing, LST. It utilizes the laser pulse of the high energy to remove the material, to ablate the material through rapid melting and vaporization. That is the first process, rapid melting and vaporize immediately. So, metal was there and metal is not there, is something immediately melt and vaporize. And then in this case, as I mentioned that this is the first process. However, we say based on the interaction of the laser energy with the material, laser ablation process can be divided into two processes. One is called a pyrolytic and a photoelectric as such. In pyrolytic, that is what happens. It's rapid melting and vaporization happens, and that's what immediately happens. So, there coming to the photoelectric process, what will happen in this case, the chemical energy whatever is really required, that only will be overcome. Maybe only the breaking of the bonds will be really required, and that is why this process is also called as something like a cold ablation. We are not raising the temperature to some extent, to significant extent, we are not really melting, we are just debonding the chemicals, and then we are removing the material from there. Now, as we know very well, laser is a very focus. So, heat affected zones also will not be very significant, which is very important, because most of the mechanical manufacturing process heat affect zone is significant, and that changes the properties significantly, and that is why we say the laser texturing or laser processes are far better than those mechanical machines. However, in this case there is also possibility, because of the whatever the heat affected zones, it can really also generate some sort of bursts and some sort of defects, and that is why we really require and the subsequent processes to remove by the grinding, polishing and lapping. So, super finish operation is really required after that. However, as I mentioned, if we are able to really develop in the future laser additive manufacturing, maybe with even the very focused one, that will turn out to be very far better compared to removing surface material from a surface, and again then we do for the polishing. Compared to that, we only add material which is very almost negligible in nanometer to micron level. So, that laser based additive manufacturing may turn out to be very good success, a big success in your near future. So, what we are saying here in this case, to make it effective manner, we can go ahead with the mask fabrication or non-mask also. However, the mask fabrication is mostly used, but it has a drawbacks, particularly as I say that we really required a polishing and all those things. Another one which is not a mask one, then we really required individual feature to be removed. So, that is why it turned out to be the it is becomes a precise, but it will be the time consuming, and that is where it has been shown over here. It is a femtosecond which is around 10 to minus 15 seconds. The pulse is based on this, and we do not really go ahead with high energy, high current, and then we give precise manufacturing. We do not have too much bursts. If we are trying to remove only small material and that very high frequency with high frequency, those are important. Now, most of the surfaces in these days are getting manufactured with this kind of laser micro machining system. You can see here the most of the cutting instrument, bearings, pistons, cylinders, implants, biomedical plants, mechanical seal, magnetic storage devices are getting manufactured using the laser micro machining system. There is another manufacturing process that is called the USM, and what is the full form of USM is something like ultrasonic machining, and this also is connected with a CNC. So, CNC has a machine and then we try to use ultrasonic machining on the machine itself, and what is really done here that the tool is really given ultrasonic motion, and then we impinge abrasive particles. So, earlier we studied that abrasive particles will cause a wear, and then we were very much worried that abrasive particle in atmosphere are really damaging the surface. So, we understand that science and use that science for our good work. We say, yeah, those process which we have understood, can we really go with a good manufacturing? Can we really go ahead with a good texturing based on that? And it has been shown here. So, first we impinge them on this abrasive material or particles, and other hand we collect those surfaces and then those particles, and possibility that we reuse those particles also. So, the CNC mounted ultrasonic machining process employs abrasive particles and vibratory tool that has been shown over here. This is a vibratory tool, and then the abrasive particle has been shown over here. The tool vibrates at the ultrasonic frequency, and abrasive the particles which directly will come and impinge on the brittle material. So, this is very good for the brittle materials, is something like ceramic, glass, silicone, which are very hard, and then they will break easily with the high impact and the impingement of the particles. We already have known that maybe at the smaller whenever there is a abrasive materials, then we should impact at the on higher angle, maybe 60 degree, 75 degree, 90 degree, and it looks like that this degree angle is also on a higher degree. Now, this is this kind of process can be utilized for the number of shapes, something like a circular shape or rectangular shape or hemispherical shape, and then dimension also can be, and then we have a significant range is something like a 50 micron to the few mm, and depth also can go to the 1 to 10 mm, but there is a possibility because we are going with a very deep 10 mm, there is a possibility the whole surface get fractured. So, we need to really look at that, what is the sensitivity of the surface towards this kind of manufacturing process. Well, the manufacturing process will be able to provide us a texture or complete breakage of this piece, right. So, that is why we say hard material may result in a micro drill failure, rendering this them inappropriate for texturing using the CNC USM, and the CNC USM can be costly also with this, because we are mounting everything on CNC, and in addition we are increasing number of accessories, and then if we really want to go ahead for the better arrangement, and because we are using 2-3 tools, collection of particle, impingement of particle, tools, motion, and maybe the workpiece motion also. So, we really require a multi-axis CNC machine, and preferably people use a 5-axis CNC machine. So, overall this turn out to be the costlier. Alternative thing is that we go out with a rotary ultrasonic machining. What is in that? It is kind of CNC USM variant, and then here they incorporate the diamond grinding, and the diamond grinding itself is rotated, and then they also generate a ultrasonic motion. So, mechanical along with the ultrasonic motion, that may turn out to be slightly less costlier, and then it really provide a more the suitable the results, and also remains a cost effective compared to the other techniques, something like we are talking about EDM, we are talking about the laser technology. So, this rotary ultrasonic machining may turn out to be the cost effective and very effective as such in performance point of view. In this series, we are going to discuss only the last process, that is what we call ECM. Electrochemical machining is basically electrochemical cell, which we already studied in our corrosion related topic. What we do in this situation is remove the material through anodic dissolution, and then we know the process will be done through electrolysis. Contour of the machine surface is determined based on the shape of the electrode, what kind of shape of the electrode we are using, that will decide what will be the texturing in the surface. And then we also do, if we use this electrolysis process, or maybe the electrolyte which has a very high resistance, then we can go ahead with a small because we are really required to give energy to remove the material. So, if resistance is on a high side and is R square, sensitivity of the resistance on a high side, so we can give a smaller current and we can get a better surface also. And then sometimes people say that we can go ahead, the electrolyte jet also can be used as a micro tool to go ahead with the localized electrochemical dissolution, and it will turn out to be more useful compared to the normal without going with the electrolyte jet. Is another good point is that this the research has been done that this ECM can be connected also with STM, the scanning tunnel microscope. That means it can really go to the ultra finishing operation. Reason being, with this kind of combination we can remove material by atom itself. So, ultra precision is possible, and that is why we say ECM can be superior to the other texture machining techniques due to low production cost compared to others, high efficiency, lack of layer affected by heat, because we do not go with the laser, so high temperature is not coming, and minimal tool fatigue in this situation. So, of course, when we think about STM, cost will go on a higher side, but otherwise it is a good. However, if it is a we really require atom by atom manufacturing, or maybe the removal of the atom by atom. So, high precision manufacturing is possible using the ECM in this situation. Now, again ECM can be done with the two ways, one is a mask less and another through mask, but more common is ECM with a mask only. That is why we say that through mask ECM is more common. This procedure involves application of the photoresist, and that has been shown here, the substrate, and then we are applying a dry film on that, and the dry film, again we are using the photo mask on this, and then we are selectively removing the material in between. That is what we are showing as surface texturing, right. So, that is what is shown here, that application of photoresist exposed to the ultraviolet rays, UV rays radiation has been also given, and then selective dissolution of the metal that follows, that has been shown, and this is a through mask which we are getting. Now, here if you go ahead with the through mask, as I earlier mentioned, there is a possibility of the edge deformation of the all the places. How much edge reduction or maybe the edge deformation can be avoided, that will give the accuracy. Otherwise, surface will turn out to be rougher surface, and then results will not be very good. So, when we go for sophisticated machines or maybe manufacturing, and particularly with a mask, so we need to really look at what will be the edge effect of those mask produced texture it should not happen. There is a more irregularities, surface roughness is increasing there itself. Now, we will just finally take a one case study, and then there will be many case studies available. In this case study, what they showed, through texture surface they try to improve the tribological performance. No? And initial surface roughness of the piece was something like a 0.5 micron, and then they use two kind of the frequencies. One is directly which is they are getting tool, which is a high frequency roughly 16.3 kilohertz, and then other one is a base which is getting low frequency something like a 230 hertz. So, this base gets a 1D the frequency response, while a tool gets a 3D response, and then what they have done basically to improve the properties of aluminum alloy, that is AL6061 T6 aluminum alloy chemical composition has been shown in this figure. And then we know very well under the dry condition or partial lubrication condition or the boundary lubrication condition, aluminum alloy will not be performing very well. So, this in this case study which has been picked up from literature published in 2022, they try to show even aluminum alloy in a worse situation can give a good surface and good performance if its texture is made in a proper way. So, just by texture change, material remains same, we can improve wear performance, we can improve friction performance, or in overall I can say we can improve tribological performance. So, what is the tool they have used? They use a polycrystalline diamond PCD cutting tool with a specific characteristic. They have used a nose radius around 400 micron and the rack angle of 7 degree. And then this the overall setup can be utilized for generating various kind of surface textures. So, various kind of texture means what will be the depth of the texture, it can 14 micron, 15 micron, 16 micron, 17 micron, and they try to really figure out which then the texture is going to give the better performance to us. And then one good point is that they were using a Strybeck curve, and a Strybeck curve is known to figure out what is the lubrication region. We say that in a dry lubrication and the full lubrication or mixed lubrication, that can be given when we know the operating point, we can figure out using the Strybeck curve based on the operating point, whether it is under mixed lubrication, under boundary lubrication, or in a full film lubrication. And this particularly in this case study, they mention very clearly they are going to use a starved lubrication. That means there is not sufficient lubrication, and we can use a word something either mixed lubrication or boundary lubrication. So, starved lubrication more preferably I will use a word boundary lubrication, less preferably or the mixed lubrication, but other than these two we can't use any other word. Starved lubrication means if it is basically a boundary lubrication, or to some extent only the mixed lubrication. To figure out what will be the friction and wear characteristics, they use a rotating cylinder on the pin tribology test, and this is one of the tests available in their lab. So, they have used it, but we can use any other test setup also, any other tribometers also. Now, what is a Strybeck curve which I mentioned? A Strybeck curve is generally given by the coefficient of there is a relation between coefficient of friction and Sommerfeld number, and Sommerfeld number is generally given in velocity term, velocity into the oil viscosity whatever they were using, divide by the operating pressure or bearing pressure. You can see here there are three domains, the hydrodynamic region, this is a mixed lubrication, and this is a boundary lubrication. So, as per my understanding what they were thinking about asperitic contact boundary lubrication as such. And then this kind of action happens when there is a low speed, high normal load and insufficient lubrication, and this is the trend. This is the trend in the future. We want to really increase the load without increasing the size. So, effective load is going to increase, effective stresses are going to increase, and then this if this operating speed is not sufficient, then naturally this will be under asperitic contact or boundary lubrication. So, would we say that the Strybeck as such, because this is known as a Strybeck curve, and often people use instead of Strybeck they use a Raymond the Reynolds Sommerfeld number or a Reynolds Sommerfeld diagram as a design tool to reduce the friction losses, because we can figure out what is the friction loss and how to really reduce it, whether we want to increase our RPM, reduce the load, or maybe increase the viscosity of the oil, and then choose the appropriate loading, moving velocity and lubricant viscosity. Now, these are the some sort of lubrication region which is not and a part of our course. So, we are not going to discuss about this. Now, they have shown this case study, they have shown close views also, you are able to see that this is a texture pattern they are able to generate on the workpiece, right. So, this is what we say surface texture operation which they are able to show, and then they are able to give vibration and a high frequency vibration, low frequency vibration, so that this kind of texture can be generated on surface. And then this is what we say the surface texturing operation was conducted using this is again they are using also CNC lathe machine, because we really require many axis operations simultaneously. So, that is why that they use a CNC machine. Of course, they had a very good CNC machine which has a resolution of the 1 micron, because when we are going for texturing you really require a good tool having a good resolution. This is a tribometer test they are showing. In this case there is a stationary block, there is a rotating cylinder. So, pin can be in the hold in this block, and then with a load it can be settled on the rotating shaft, and that in this case they apply the load, two loads basically 10 Newton load in one situation, 50 Newton load in another situation, and then they use the different rotating speed 100 rpm to 1000 rpm, and then so that the plot on the Strybeck curve can be plotted easily. So, they what they use on the lubricant, they use a VG68 the viscosity grade oil. VG68 is something like 68 itself here it gives the viscosity of the lubricant, and the kinetic viscosity of the lubricant is something like 68 centistoke. So, VG grade itself is providing the what will be the viscosity of the lubricant itself. So, whenever the sample, and then because for wear measurement you need to clean the sample also. So, they have given the process, they used to clean them using acetone and then dry that before going for experiments, and then this is the table which has been shown the conditions. This is the tribometer cylinder on a pin setup they are showing over here, and this is to plot the get a Strybeck curve. And then they in this diagram they have shown different textures, and then you can see here the 14 micron texture, 15 micron depth, 16 micron, 16 micron, 17 micron, and then x and y is the same 0 to 619, 0 to 453, same 16, all the things they have given the same article, only the vertical depth has been changed, and that is why they use case 1 14 micron, case 2 15 micron, case 3 16 micron in the surface, and then coming to the case 4 is more or less also same, only thing in this case they have expanded to the 387 instead of 319, and keeping other dimensions same. Case 5 they have kept a 617. So, the as we are going from downward direction or going from case 1 to case 5, dimension of this dimples are increasing. So, the depth is increasing and maybe one dimension is also increasing. And then they have plotted this curve, you can see the curve for this curve, and then they compared something like a hierarchical texture or single scale texture. Single scale is that means almost all the dimples are the same size. Hierarchical is something like there is a mixture of these, and keeping making single scale texture is naturally very difficult, and we go ahead with hierarchical because sometimes we required a shallow texture, we required something deep texture, because of various condition one will prefer compared to other. So, that is why we go preferred mostly the hierarchical one. Now, again in the first case where the load is low is something like a 10 Newton, we are able to see the complete Strybeck curve. You can see here that increasing in the first it is decreasing then increasing, right. And in my view, particularly for the friction point of view, we should not go with the texturing, because texturing is going to give only worse performance from friction point of view. And that has been shown here, that this is the non-textured surface, the right color, it has been showing the best performance. Same thing in this case also, whether you go with a single sketch texture or hierarchical texture, in both the cases, if there is a low load, we should not go with a texture, particularly from the friction point of view. However, I am not using still the wear point of view. Wear point of view, we need to really see whether that will be preferable or not, but from friction point of view, it is not really required. Coming to the higher load, that is a 50 Newton, you can see here nothing is going in a strike back curve, and this is basically on a starve condition or boundary lubrication, still it has not gone to the downward direction. And here you can see here the non-texture is showing a worst performance. While coming to case 2 in this case is showing the best performance, while in this case case 3 is showing a best performance, right. So, it depends what kind of performance. Of course, the data are not very good in number, we can't conclude based on that, but one clear thing is the low load case, effectively low load case, we should not think about the texturing, but in a high load case we really require texture, where there is a possibility of the starved lubrication. Now, coming to the wear point of view, the wear point of view, here it is shown the 10 Newton and the 15 Newton. You can see here in the case of the non-textured surface, everywhere it will be naturally will be constant and it has a high value as such. So, case 1, even single scale texture is causing and the single scale texture is causing higher wear rate, even hierarchical is also causing a higher wear rate in case of the 1, right, the depth is not sufficient. Coming to the case 2 and 3, and the case 2 is also showing a similar kind of performance, and particularly case 2 hierarchical is going worse performance compared to the non-textured one. However, in case 3 the behavior is significantly different, so preferable, right. So, this case 3 or maybe the case 4 are preferable compared to the case 1 and a case 2. So, we should have a slightly deeper the texture compared to the shallow texture in this case. When we go to the applied with the higher load side, everywhere the texture is going to give the best performance compared to the non-texture. So, from this one we can conclude that whenever we have a severe load, actual case, then we can go with the textured surface. When we have partial one or maybe the load is not that severe, maybe texturing will unnecessarily cost more and it may not give that kind of fruitful results. So, texturing also should be done judicially. It is not that we know the texturing, we will start doing a texturing. It is because it is going to be costing cause additional cost, manufacturing cost, and if it is not really giving significantly good performance, then we should not go ahead. However, texturing is one of the very good effective method, and if the texturing is not really giving the overall good results, we will go with other surface engineering technologies, so that we get a better and better results. Thank you for attending this lecture. Thank you.